Hello everyone, welcome again to today's seminar. My name is Jimmy Hu. I'm a chartered HPC consultant based at the University of Waterloo. So today I'm going to talk about MPI-IO, advanced features. So we have a talk, another seminar a couple of months ago, introduced into parallel I/O, and we talk about the basics in MPI-IO. So today I will start with a brief review of the MPI-IO basics. And build on top of that, I will continue to talk about some advanced features. Parallel I/O, on main purpose is to deal with a very large data set while running massive parallel applications on supercomputers. As we know, for parallel computing, we also want to deal with some things like want to improve performance, and certainly we want to have it's reliable and it's portable or it's scalable. So all those things and sometimes are not trivial and will takes time to do it, or sometimes we cannot do all of them. So we have to make a priority. So that's why there's different solutions to manage I/O in parallel applications. Regardless, the basic thing is at the program level, so user will need to do concurrent reads or write. So that will be from multiple processes and then write to a common file. At the system level, we need parallel file systems and the hardware and that support such concurrent access. So when we talk about I/O layers and parallel I/O, we always start to look at this diagram and to have a better understanding the basics. So at the lower level is a parallel file system. So parallel file system which will enable the actual parallel I/O operations. Nowadays, all the file systems like on our clusters, we use lost file systems. It's a parallel file systems. And then like IBM machine, they may have used GPFS. So anyway, and the file system itself is ready for us to do parallel operations. And then in the intermediate level is that a portable operating system interface. It's called a Pocket system calls. And then the other one is the software level, and it's library based. It's MPI, it's MPI-IO. And, and on top of that, and there's already well available high-level libraries like the parallel HDF5 or the parallel later CDF. So those are basically based on MPI-IO library and then POFIX and build the more highly available libraries and for applications. So when you're doing MPI coding, so basically we need to understand MPI-IO and if we do MPI programming and do it. And many commercial softwares and they actually never use HDF5 or LetCDF, and because that may be more efficient, and then sometimes and coding MPI-IO is not a trivial thing. We talk about the different ways in parallel applications, and then the focus will be we have all processes to write to a common file. So that's the key here. So we don't know about the other sequential things, and each will write their own files. That's still the ways or one of the other ways and in MPI-IO. So here the diagram will give a sort of understanding is here. It's basically each process and they can write their data to a file, and there's no communications between the processes. So this is called independent writer. And the independent writer, and certainly synchronization will be needed, and certainly, and sometimes they may have some issues in terms of the conflict or some log, some things. However, this is a fundamental. It's basically the way. It's basically MPI, where now each process can write to a specific portion of the file. And not necessarily is a contiguous way, but this diagram basically show a file view is a contiguous way. And this is basically the major part of the libraries, even like parallel HDF file and the latest HDF file. The company use this type of approaches. And then the other one is more favorable and certainly is more complicated. It's called connective writers. So these connective writers, as shown by this diagram, is a set of processes. They may communicate each other, and then they will do a sort of data aggregations. And then not all the processes issue the write, and instead they will choose processes or write the connective data to a file. So this is certainly should be more efficient, and the purpose is to do it in an efficient way. And certainly sometimes it may be difficult to implement. The higher level libraries, they can make that type of this type of operations, and without us to basically know the details and how to do the aggregations. So that's why in MPI applications, and if you have a high-level library to use, you may like to use it. Okay, so back to MPI-IO, and it was introduced a long time ago in the MPS2. It's a set of extensions to MPI library that enables parallel high-performance I/O operations. So it provides a parallel file access interface that allows multiple processes to write and read to the same file simultaneously. So what we talk about today will be some of them, and then say we will briefly bring up that contiguous or non-contiguous I/O, individual and connective I/O, as we showed in previous two slides. So the I/O, and we talk about it, say, is I/O to one file instead of to many files. So MPI, this library, and it provide a portable programming interface, so that it will now efficient data transfer between processes and potentially and good performance. Okay. So when we talk about and we learn or study MPI-IO, your basic concepts are quite important and will help us to understand, particularly when we bring up the MPI-IO API syntax. The first thing is the file handler. File handler is a data structure which is used for accessing the file. And another is called file pointer. The pointer is a position in a file where to read or to write. So that will have a function call, and for each process to understand where to start to read or to write. So the file pointer can be individual for all processes or is shared between the processes. It can be accessed through the file handler. And then the other is the file view. That's the part we'll cover today. So file view is a part of a file which is visible to process. So it will enable efficient non-contiguous access to file. And then in terms of the command, and we will use will mostly will be introduction level is individual I/O, and the high level and advanced will have a bunch of connective I/O operations. So connective basically is MPI coordinates the reads and the write of processes. Individual, as we said, there's no coordinations, there's no communications between or among those MPI processes. So the basic MPI operations we talked about last time, and we put it here as well. So basically, the simplest way we need to use in a program certainly is a file open, and then the file seek. That's where basically deal with the file pointer to where to find locations or offsets for a process to read or write. And then certainly the read command and the write command. And once it's done, and we come to a close, the file close. So open and close are connective operations on the same file because this is open and this close will be operated by all processes. And the read and the write are similar to, MPI send a message or receive message. Is basically where is a data to read from or write to above, and then eventually will go to a file. So each MPI process has its own local pointer to the file, so individual file point. So for the seek and for the read and the write operations. And we have offset attributes or variables is a particular kind of variables and is given in elemental units called E-type and to access to a file. And then it is possible to know the exit status of each subroutine and the functions because the status is a part of that function call. Okay, so now we can quickly go through the basic APIs. So the first one is file open. So this file open, so you can select attribute. So it's a connective call for all processes and communicators to open a file. So the first one is that is COM, is a communicator. And by default is the common word. And certainly you can define your own communicator. And then with the file name, and then is the process access mode. So in this mode, you will know you open this file for what. So you can could have a read only, or you can have a write only, or if it's a new file, you have to create a new file, or you open this file is for read and write both. So different mode you need to specify it when you open a file. And then is the MPI info. Info is a hints to implement for optical performance. You want to have a better performance. Otherwise, you always no hints. You just use MPI nar. And the file handle is a part of pretty much for all of that MPI-IO operations. And then the file state, as I said, is a file pointer. It's a position in a file where to read or write. So it can be individual for all processes or shared between processes. And each process will move its own local file pointers. So this is the syntax. So basically it's a file handle, and then you need to tell the displacement in bytes and for which processes to where to start. And the lower get the portion of the files for them to read or to write. And the ones is basically is a set sig set. This is basically to set the offset, the pointer to set to offset. It has other attributions if you want, you can use. And then is the file read. And the file read is at individual file pointer. And this is the file handle and the above and where you can, in memory, where to read the data. And then the size of the data to read is the count of the elements to read. And they have data type and the status. It's similar to that status MPI receive. And then we have the write. And similar to reading, when you need to open a file to be ready for write. And then so you either open it as a write only, or if it's a new file, you need to simultaneously to to use the mode is create and write, or you create, read, and write. So it's similar to the write, and then the read. Write is the file handler, and the buffer. But the write to and the count is the size of the line buffer. The element is to write to, and the data type is either is integer or is a character or something like that. And then that is a status. So it will update itself the position of file point each time after the write. Okay. So here is a super simple and explanations for how those commands will work, and then how you can actually put them together in a simple file. So here, for example, is a parallel read is a simple file, and you simply change the read to write, and you can the other way you can. It's basically is quite similar, maybe not exactly, but quite similar. So what this piece of code is going to do is say we have a file, we have a data file, right? And assume we use 4 processors to do it. And then the total data size is like this. And then we hopefully we can divide it to 4 different buffer size. And they certainly you have a way to do it. And they basically is say the total file size divided by the number of processors, you will get that buffer size, right? And then you have to find the offset and the startup displacement. The first one will start with 0. And then you have that offset. The second one will start with that 0 plus that offset for 6 processes, and so on. And then certainly is you define the MPI file status, and the open command is certainly your command. This is your default communicator, and assume this is your file somewhere. Its name is a data file, and then you open it for read. For example, just read only, and the default info. So this is open command. You need to open this file first. And the offset, you calculate offset. And the offset, for example, you get the size, the full size, and then you can calculate the buffer size. And then you can, well, if it's integer, for example, here, you can calculate each buffer size, how many units there. And then there's the amount of data there. And if you have that, you can define it. So you can file sake, define it is each will start from where? From 0, we start 0. The second one will start from buffer size, start there. The second one will start at 2 times the buffer size, right? And this is for each to start. And then you can read. You can read the buffer, you can read the size, is the count. And then that's it. And when once done, it's closed. And if you run this code, if you have a data file, certainly will display it, and will show you is a parallel thing. Okay. So now we can move on, and we call it some of them is advanced features, and may or may not, and certainly is not all of them, and certainly we just cover some of them and some basic of them. So this will certainly will come to talk about is the contiguous or with non-contiguous I/O, because in coding side we needed to decide it and then how to implement it. So in the contiguous I/O, it's easy to understand as demonstrated by this diagram. So it's basically each process and it's move data from a single memory and block to a single file region block. And it's contiguous and sort of a sequential way, like I say, start with the process and I/O. The ID is 0, and then it's 1, 2, 3, and continue. So like that is this type of patterns. And the more common one is the non-contiguous I/O. And we normally talk about is the contiguous in file. And however, by definitions, it could have 3 forms. So like it could be non-contiguous in memory, or non-contiguous in file, and non-contiguous in both. We're not going to go to the detail, but here we basically show with non-contiguous in file, and then each processes will write the partial data to him, and each will come to certain of patterns, and then basically repeat and repeat those and lead to a whole common file. And the normally structured data will lead naturally to non-contiguous I/O, and like that. Okay. And then we talk about the file view. And the file view is a file it defines which portion of the file is visible to a process. So each process needs to view part or specific portion of the file to be able to read or to write to the locations. File view define also the type of data in the file, and it's a byte or integer or float, the data type. And by default, file is treated as consistent of byte, and the process can access, read or write any byte in the file. Okay, so before that, we talk about the default, the basic one. We didn't talk about the file view, and it's actually the default file view. And the default file view is for each participating process. It's defined implicitly while open the file. In that case, there's no displacement. The file has no specific structure, and then all processes will have access to the whole file. It's not just a portion or part of the file. Okay. So we'll use a few slides and try to explain the file view and hopefully logically make it easy to understand. And the file view consists of 3 components, as demonstrated here. So the first one is the displacement. Displacement is the number of bytes to skip from the beginning of the file. It's where the starting point if you have a displacement. And then is called E-type. E-type is a type of data accessed, and you define the units for offset. And then is a part is called file type. So file type is the whole like the file type is a base portion of a file visible to processes. And it's actually the same as E-type or MPI derived type and consisting of E-type. So from here, we have that E-type is like we treat it as one part of the file type. So in this file type, it's actually we have, say, we have 4 E-types. And then the start with the first one is a gap, is a hole. And then have 2 is real data. And the other 3 are holes, are gaps as well. And then the whole file may be treated as this type of things, like we'll start with the displacement, and then there's a file type, and then there's a continue and repeat, and so on. So this simply view is something like this. And then if we from a multiple process point of view, it's something like this, and this is a logic view. Anyway, it's not like a real example. So we show next slide. So for example, we have a communicator of MPI process. We have a file. So we use different colors to spread it. And then the logic of view or something like that. Each of them will write part of the data and the start. And then this basically is like called the file type in the file view. And then they basically the tiling this and continue until the end of the file. And then this will write physically to a disk. Okay. So we use this example is say 3 processes here. And then this each will be a E-type, it means the data type, right? And then the first one is a file process is 0. And the file process for 0 is just 1 and the data. And then they have 4 gaps there. And then the second process, say, assume they have only 1 E type here, and then they have a one gap ahead and three gaps afterwards, and then process third one or something like this. So if I have this file type, and the whole file type will be 1, 2, 3, 4, 5, will be 5 units. And then if we tiling the file together, if something looks like this, we'll start with a certain displacement, and then will be 1, 0, 1, 2, 3, 4. This is one file type, and continue. So from the file viewpoint, file view to see the file view for process, the only say its own is let's say the first one, then skip all the gaps, never take the second one. So the first process will say 0, 5, and the second one will say 1, 6, and the other one will say the rest. Let's define the file views. Okay. So based on this, we can come to that API to easy to understand those contributions there. So MPI file set view. So we start with file handler, and then it's display is that displacement is offset from beginning of the file, right? Or here we always start with its in bytes, and then start with that E type. Its type is basically MPI type, or if either you defined. Otherwise, it's basically we call it E type. It's a unit of E type. And then it's a file type we talked about just now. It's a type, E type, or user defined. You can use defined. We'll cover that later. So it's basically which part of the file is visible to your process. And it comes with other, it's called a data representative. So this is a string that specified format in which data is written to a file. So normally we'll use native, because native is basically what type of data you just write it to a file. Or you can define it as internal or external 32. And that may make it a little bit more portable if you write it on different systems. Or you can use the defined, whatever. Info is the hint, and we'll cover this a little bit briefly later. And in most cases, we don't use hint, and use hint purpose is want to improve the performance. So like we want what's the 32 digits or 64 digits, or you want some other, how many stripes, how many file stripes to use, something like that. Okay. So this is a set of file view and set it correctly, or you can use your self-defined file types, and then you can pretty much do whatever you'd like to do. And in addition to set of view, you can, when you open a file, you can actually get views, and say the run the process of view of the data to say what's the what type of we use it. Okay, so we come first with this the simplest example. Here, from the output, you can say this is a user file set of view to do a sort of contiguous data write. Okay, so what this piece of code doing is say we said our offset is 10 each, or element is 10. And then we each will assign a number, or we call a character here, okay. And then with that its index, for example, 0, you will create an array of index, the size is 10, will be 0. And here, for example, use 4 processes, and the ID will be 0, 1, 2, 3, right? So when we do this, and basically we say we open a file and we name it as data, right? And this is a new file, so we use that mode create. In the meantime, we open it for writing. Okay, and we'll calculate offset. So offset is a displacement, okay? And the first start from 0, and the second one will be from rank 1 will be sizes of is 10, each with 1. So we'll start with from the tens, right? So each will depends on the rank. They will know where to start. And then we have the set of views. The display is defined here, and say we use character is the size as a character, okay? And we write relative whatever write it, and then we write this array, and each will write the size is 10. And so if you run this piece of code, and then it will, if we print out, you check the file, this data.out file, this number will be, and there, this will be the results. Okay. And then the other one is somebody explained is for that non-contiguous data replications. This is the more common case, and certainly is a little bit more complicated. And we're not going to the pretty detail, but just give you the explanations. So for here, we know, and so this pattern will be start with a sort of displacement. And then we know in this case, the file type, well, basically is stride is 6. And we assume it's 3 processes. So these 2, the first one start with the red will have 2 and E types, and then you have the second one will have 3, and the third one will have 1. So it's basically this will define MPI, and the file type is contiguous with legs 2, 3, and 1 each processes respectively. And then it's basically replication of this file type, right? In this case, where it's basically each process will need to resize the type, adding holes on the right, so how many holes to follow. And then each process will need to determine the displacement, and then each will start with, for example, the first one will start from 0, the second one will start from 0 plus 2, start from there, and last one from 0 start from plus 5. So you can say the file size here, for example, you're coding here, you can say a count process each will be, the first one is 2, the second one is 3, and the third one is 1. And the displacement will always have that add up things will be from 0 to 5. And then you can create that count it, and then you can do the size, create the size, and the total will be 6, right? And each will contain that. And you can calculate offset, use this displacement to calculate offset. And in this case, what you do here is actually you define your own file type. And you define your type, you resize it is basically the count there, and with 6. And then this is a new file type. And then you have these calculations, and the set file will be like the offset you calculate from there, and then and the E type is integers, assume it's integers here, and the file type is what we defined here, okay? And it's relative and whatever. And each will write its own data to the place, locations, or defined here, right? So what we talk about just now is a file view, and file view, particularly in this case, we bring up some new things like some other function calls, and particularly you can define your own data type. You can define your own file type. And then this comes with the other thing is called MPI derived file type or derived data type. And we list a few of them here, and like the type contiguous or label create resize, that's already used in previous slides. And we're in the following, and we'll bring up that type of vectors or create subarrays, and basically to demo there's some different ways, or there's more ways to deal with a data structure, and make it may run a little bit faster, or make it maybe more efficient in doing the parallel MPI-IO. Okay, so The first thing I want to bring it up to that API for MPI type vector. So you can vectorize an array or a matrix. You can vectorize it, right? The same concept. And it's basically it's like a more generated constructor that allows replication of a data type into locations that consist of equally spaced blocks. So each block is obtained by concatenating the same number of copies of the ordered type. So what the contributor here is say is the count, is the number of blocks, and the start. And then the size, the block length, the number of elements in each blocks. And then the stride, the number of elements between start of each block. And then it's type. So this is the syntax. And we use this example to demo it, and you may understand it better. So assuming we have a 2D array data file, and then we're assuming it's distributed column-wise. And what does it mean? It means basically, say, if we say we use 4 processors, for example, the first one we own the first column, the second one is the second column, and so on. Okay, and then this in say this is the data file, and then when we approach to it, and so MPI, and they can write in this way. So in the memory is always in in array type of structure, right? We can define this array as a vector, and then you can say it's basically it's basically saved the file is like is in a fashion, and the word starting from 1, 2, 3, 4. This is like a file type, and then is replicated. And so in this type, for example, it's 4. It's basically the size is the count is 4, and each word has 1, and then you will have and buffer subset is 4. So this is count for that, and then you can define that that as a in this API. So what we have is count of 4. We have buffer. So you can create from this to the array to this MPI type, and you define the list is type, and then you can commit this is a file type now. This file type is a vector, and the vector is this type of structure, right? And then you have this. You can set a file view. You have display, and this is missed. It's not showing in this code. In sample code, you have this type of file structure, and you have this. You can do that the writing to write this in this fashion. Okay. And for the same type of data structure and to the array, you can have other ways to do it in MPI. It's called subarrays. You can define subarray, and in that syntax, and so certainly different size, different attributes. Basically, it's going and integer is a dime there, and then the total size, the sub size, and where to start, and then could be able to, to divide a total, a big array to the array to sub arrays, depending on how many processors to access it. So we don't want to spend too much time here, and then here basically we give you a demo to say, for example, in this case, we decompose the 2D array to subarrays. Again, we have 4 processors, and each will be, so this is 4 by 4, the total data structure. And assuming we have your 4 processors, we each will do a 2 by 2 and the subarrays. And in this case, or in the memory, in the file, it will be something like this. This type of, certainly will be this type of structure. And then this way you can create this. And the way it's you need the total size is 4 by 4. Your subsize is 2 by 2. You can define it. And then you can the coordinate and you know where to start, and then you create that subarray. It's basically created is each word size will be 2, and the total size is 4, and the subsize is 2, and you have the start from the coordinate you will know it, and you have defined this basically is the file type you define, and this is basically you can set up this view, and then you can do the write. So what this is basically say you can have your own defined data structure to do and read and write, and not necessary to just do one by one. Okay. Okay, the next thing, and I want to briefly bring up that hints. And the hints, as we said, the purpose you want to improve the performance, you have a way to do it. And let's basically show in that file open. When you open a file, you can have an MPI info, and for you to add something to it. And then set a file view, that's a part of it as well. And these basically allow the user to provide information on the features of the file system employed. So it may enable the implementation to optimize the performance. So most cases, like examples I used, basically is no, you basically use now. And you can use that function info create or set to allow to create or set hints to it. For example, if you can use the hints in variable to set up things, or you can set up, say, what type of way to do it. Like, for example, you can set a data type in this data, or want to do connective I/O, aggressive, and set it to 32 load, or how many load to use. So this is the other way to do it. Okay, so there's quite a few and MPI function calls to do the hints, and yeah, like you set up a stripe. So we want a loss structure to use 4 disk arrays instead of 1, and something like that you can set up, and you can have others as well. Okay. And for example, this is quite a simple and function calls like demo it, and we set. You can set a stripe, say for example, it's 4, use 4 stripes instead of 1 by default. And you can say for stripe the units, so the size, how many bytes, and the list bytes. That will define the format and of your file, right? And you can say, in this case, you can open a file, and you have the file there, and then you can have that info. This info is you set this info, so this info will be something you set it here. Afterwards, you can free it, go back to default. Okay. So now the following I will run it quick, and basically we covered the independent or connective I/O, and so this is basically not a. Sometimes you will do and the process do independent I/O. Sometimes you will do connective I/O, and it depends your need, and it depends of that data dependency or something like that. So the many applications have alternative phase of communications, and they may be doing I/O phase. They can also read and write data, or they can connectively access storage or something like that. Okay. And the connective operations, the function calls is pretty much the same, and just add to that underscore all. So if you have that read and write underscore all, that means you are doing a connective I/O. And because that others, so for the individuals, that means each will do it individually. That's individual function call. So that's the only difference in that blocking and general options. And then the other one is blocking or non-blocking I/O. And we have blocking I/O. It's just like the read and send, receive that. You could have blocking I/O. You don't need to wait and log and non-blocking. And blocking, you need to have a sort of return. And the difference is the similar is if you have the all, syntax or that function calls them as I, start with I read, I write, or I read at all, or I write shared something. So that means you are doing non-blocking I/O. When you're doing non-blocking I/O, you need to issue MPI wait, and that for the synchronizations, something like that. Okay. And then there's you can do conductive non-blocking I/O as well. In this case, and you do it in two parts that are called split connectives. So you have that there's function called read, say, or begin, and do some things, and then the read or ends. And they have relatively like a write similar comment as well. And then the other you have say consistent operations. Say sometimes you need to do it atomically, or if in case you need to issue that synchronizations calls, you can have it as well. Okay, so these are not something I I will cover in detail. I think that is pretty much for today, and it's brief. And you talk about advanced features, still sort of introduction levels, and certainly MPI library function calls, there are hundreds of them, and MPI there's more detail of them, and hopefully this is help you to read them and to start if you want to go your own path to do when you're doing MPI parallel programming. Okay, so some of my slides, particular diagrams, we take from that some online tutorials and online and documentations, and or use it and reference table. Okay, I think that's all for today. Thank you, everyone.